All right. Well, I'm glad to see everybody made it past the big storm we had, all 8 to 12 inches of snow. And if you guys are anything like me, I'm sure you thoroughly enjoyed shoveling your driveways out. Though I think I was relatively lucky. Yeah, my snow blower is big enough to handle it. Didn't take me about an hour and a half. So maybe I lucked out on that. But certainly felt it that night and the next day in my back. One of the benefits of getting older. So anyway, without further ado, I guess let's go ahead and get started for the day. So you should have read chapter 3 in the textbook, okay, and also watched Earth Revealed videos 14 and 18. Okay, so that will have prepared you for today's lecture so we can go a little bit more in depth and talk about rocks. Okay, so before we get started with the lecture, are there any questions? Any questions on anything? Okay, not hearing anything, I'll go ahead and switch over to PowerPoint. Okay. Hide. Alrighty. All right, so today we're talking all about rocks, okay? Okay, the first thing that, the most basic thing, I guess, I want to everybody understand is the different types of rocks, okay? Really, rocks are just broken down into 3 different categories, okay? And then we'll talk about different rock names inside those 3 different categories. Okay, so first we have igneous rocks. Okay, these are rocks that are produced from magma, which is molten earth material, so basically melted rocks. Or igneous rocks can be produced from lava, which is also molten earth material. It's the same exact stuff as magma. It just has a different name because of well, and to explain it easier, lava is molten rock that basically exits Earth on Earth's surface. Okay, so magma is molten rock that's below ground. Okay, basically stored below ground. So really, it all starts out as magma, and then when we go to talk about like volcanoes, that's when lava comes into play, where you have magma that begins to discharge upward towards Earth's surface. Once it discharges at Earth's surface, then it officially becomes lava. Okay, but I just want you to know 2 different names for the same exact stuff. Okay, then there's sedimentary rocks. These are rocks that are formed from the compaction and cementation together of what's called weathered and eroded sediments. So we'll look at the concepts of weathering and erosion later this month, but just know for right now, weathering is essentially the chemical and physical breakdown of earth material, so like rocks on Earth's surface by the environment, okay? We know that rocks break down into smaller pieces. Okay, they break down into sediments. Okay, sediments are those small pieces. Okay, and then once they break down, usually there's some sort of transportation process, such as water. Okay, water is very good at transporting like sand, silts, things like that. So that transportation process is referred to as erosion. Okay, so putting that all together, sedimentary rocks produced from compaction and then later cementation of weathered and eroded sediments. Okay, so we'll talk more about that later. And then lastly, metamorphic rocks are kind of a category of their own, where these are, all metamorphic rocks came from existing rocks. Okay, So in order to have a metamorphic rock, you had to have a rock that was already there. But what makes it metamorphic is that you take an existing rock and you add heat and pressure to it over a long period of time, and then the heat and pressure basically changes the composition of the rock to make it metamorphic. So those are the three different types of rocks. Okay, didn't know if we had something in the chat there. Okay.
Yeah, that was me. I had a quick question.
Oh.
So
yeah, go ahead.
So with metamorph, you said add heat and pressure to change rock, right?
Correct. Yep.
And then what did you say for sedimentary?
So sedimentary rocks are produced. There's when you get sediments that are compacted and then cemented together.
Okay. So it's just like combination rocks, like they're combined into one rock.
Pretty much, yeah. You get larger rocks that are broken down by the environment into smaller pieces. They get transported somewhere else into basically big piles, and then those piles, they basically get cemented together into a different but larger rock.
All right.
Okay. Yeah. So we'll talk more about it a little bit later in this chapter. All right. So first, let's look at igneous rocks. So igneous rocks can either form at Earth's surface or below Earth's surface. Okay. So when rocks form below Earth's surface, that's referred to as intrusive or plutonic. Okay. I guess right now I'll just take the time out to explain why in geology you'll often see two terms to describe the same thing, like plutonic and intrusive. Okay, that is because when geology was a young science in the 1800s, before telephones and all that good stuff, the disciplines, geology basically was on two separate tracks, one in Europe, one in North America. And so each location came up with their own different terms for the same processes. Okay, so hence the two different terms. You'll see this happen a lot in the geology part. Okay, so intrusive or plutonic, that means that those igneous rocks form beneath Earth's surface. Rocks that form on or at Earth's surface are called extrusive or volcanic. That's volcano. These are formed, extrusive rocks formed from lava, okay? And just remember, lava is just simply magma that has come from below ground and moved upward and discharged at the surface. And once it reaches the surface, it changes its name to lava. Okay, so here's kind of a diagram look at, is your question?
Yeah, could you go back really quick just for like 2 seconds? All right, thank you.
Okay, so here's a diagram showing intrusive versus extrusive, just kind of a side view, like cutting Earth open and looking. You'll notice that volcanoes are considered part of the extrusive, so at Earth's surface. And then you have intrusive down here below Earth's surface. This is where you often contain pre-existing rock and then these big blobs of magma, which are these orange and yellow colored deals. Okay, those are, yeah, just basically big blobs of magma. We often refer to them just as magma chambers. But yeah, basically, this is where the lava comes from. It comes from the big lava or magma chambers beneath Earth's surface. And then those are what supplies a volcano for an eruption. But basically, yeah, you're seeing these two different environments that igneous rocks form. And over here, you look, these are 4 different types of rocks that can form in those environments. The top 2 are extrusive, the bottom 2 are intrusive. Just notice right now that they're different, okay, especially their grain size, okay? The grain size is the big thing to keep in mind. These two that are intrusive have larger crystal grains or mineral grains. These two at the top, well, this A is kind of an oddball, shouldn't really be in there, but B has very fine mineral grains. So we'll talk about that now. That's called texture. And texture is just simply size and arrangement of crystals. And really, the term crystals can be used interchangeably with mineral. Okay? Mineral, crystal, essentially the same thing. So typical classification of igneous rock is based on the texture, but also the mineral composition. So we'll look at those two differences as well. Okay, so the first texture is coarse grained. Okay, coarse grain, which is represented by this rock here, this is granite. This is a very slow rate of cooling. So this rock forms, it solidifies from solid, or from liquid, liquid magma over a long period of time, tens of millions of years usually, if not more. Okay, so what happens during that slow rate of cooling? Well, what happens is because the cooling rate is so slow, that gives those individual minerals plenty of time to grow larger in size. Okay, you'll see that when we look at the next texture, where they're fine grained, that's not the case at all. Okay, but with coarse grain, you have that slow cooling rate, which allows below the surface, which allows the mineral grains to grow large in size. Fine grain mineral texture is a fast rate of cooling, and those form at or very close to Earth's surface, where the rate of cooling is quick, and as a result of that very quick rate of cooling, those minerals don't have much time at all to grow in size. So they pretty much go from molten to solid very quickly and don't ever get the opportunity to grow in size. So with fine grained textures like this rock here, rock B, you can see that it looks like it's one solid kind of color, but in reality it is individual mineral grains. It's just that you can't really see them with the naked eye. But if you look at them with just a hand lens or a microscope in thin section, you'll actually see the individual grains. They're just very tiny. Okay, so remember that these fine grained textures associated with extrusive igneous activity, so activity at Earth's surface. Okay, then there's something called porphyritic texture. That's rock C here. You'll notice that it has a combination of large crystals and small ones. Okay, so that's kind of a unique situation, and here's how that happened. So first, you had a rock that formed deep below Earth's surface. Okay, so an intrusive igneous rock. It was down there for a long time. Okay, so you can see that some of the mineral grains grew very large in size, large enough to see them with the naked eye, but not all of them. Okay, so we know that at some point, after being down there for a long time, this rock found its way up closer towards Earth's surface, or even at Earth's surface. Okay, and how that happened is most likely through mountain building. Okay, so mountain building, which we'll talk about in another chapter, and also plate tectonics, those are really the processes that basically drive rock that's deep down upward. Okay, think about it. When mountains form, you get land that's buried below Earth's surface that's driven upward. So rocks that were once buried deep down suddenly, after a short time geologically speaking, find themselves at Earth's surface, or even above Earth's surface, ground surface. Okay, so they're exposed to the environment. So at that point, now that they found themselves close to Earth's surface or right at Earth's surface, that's when the grains really don't have much of an opportunity to continue to grow. So they pretty much solidify very quickly, resulting in the rest of the empty spaces kind of filling in with those small grained minerals. Okay, so the overarching conclusion is with porphyritic, the rock cools slowly, then it gets moved up toward the surface, where then it finishes cooling very fast. Okay, and then a couple other types of textures, igneous textures, are glassy. So glassy textures represent a very fast rate of cooling, almost instantaneous. Okay, this is basically material that has been discharged from a volcano. Okay, so usually molten lava. Okay, so the orange colored stuff literally being shot out of the top of a volcano and being solidified pretty much instantaneously into solid rock. Now, the quicker that lava solidifies in the air, the smaller the grain size is going to be. And so when you look at a glassy texture here, what you're actually seeing is literally glass, because this is how glass is formed. Okay, glass is just made up of silicon dioxide, just like the silicate minerals are. Okay, and so basically that is to say, glass is essentially quartz, the mineral quartz. It's just very fine sized. So it's so fine in size that you can see right through it because obviously it's glassy. Okay, so very quick rate of cooling. Okay, and the air plays a large role with that. The air cooling it down very quickly. Then there's vesicular texture. Okay, that's basically a very similar formation as glassy texture, where you get some liquid liquid molten magma discharged out of a volcano. But this specific type of magma tends to be a little bit thicker than the glassy stuff. The glassy stuff tends to be thinner. And we're going to talk more about that when we look at volcanoes. But for now, with the vesicular texture, I just want to say that since it's a little bit thicker, a little more viscous material, what happens is it gets shot up in the air. It solidifies pretty quickly, just like the glassy texture. But the thing is, because it's thicker lava, thicker lava just naturally tends to have a lot more gases in it. And so what you're seeing here is all these little holes. Those are actually gas bubbles within the trapped within the rock itself. Okay, so and then the white constituency is made up of individual minerals as well. Again, because it was because it solidified so quickly, you can't see those with the naked eye either. You would need a hand lens or a microscope to see those as well. But the interesting thing about vesicular texture here, like I said, is the gas bubbles, which is clearly identifiable. That's the easiest way to identify that texture. But there's a rock called pumice, okay, pumice, which you're seeing here. It actually floats in water. It's so light that it's lighter than water, all those gas bubbles. All right, so that's a look at all the different textures. Are there any questions on the textures of igneous rocks? All right. Well, then let's go ahead and move on to composition. Okay, so we're going to look at different compositions of igneous rocks. And just off the start, I want to tell you that the way we're going to classify these is based on silica content and mainly metals content. Okay, but silica content is going to be the biggest thing. And what you're going to see is as we go through these, you're going to see the colors of these rocks, the general color scheme, go from lighter to darker. Do you have a, okay. our intrusive rocks, large and extrusive. Intrusive rocks are large, intrusive are small grain. Yes, that's right. Intrusive rocks have those large crystals. Extrusive rocks have small crystals. Okay. So yeah, we're going to look at the different compositions, and you're going to notice that we're going to go from generally lighter colored rocks to generally darker colored rocks. And there's a method to the madness that I'm going to explain as we go through. Okay, so here you can see the lighter colored ones, dark. This one is an exception that I'll talk about, and these are the part of the dark ones. But anyway, so granitic rocks, okay, these are also referred to as felsic, okay, because of their mineral constituencies. But basically, these are high silica rocks and low metal content rocks. Okay, the key, like I said, is high silica content. Okay, so the main mineral constituents are quartz and feldspar. Quartz being the colorless to kind of white-looking one. Feldspar is this kind of tannish pink one. And then you can, of course, see the black-colored one. That the black one varies, so I won't go into that one to tell you what the types are. That's not really that important. But what are important really is the light-colored minerals. Okay? So high silica content, and then what you're seeing are one extrusive version, which is granite. Sorry, one intrusive version is granite. Okay, so granite, you can clearly see those large mineral grains. Okay, with the naked eye. Then you move down here. Rhyolite is compositionally the same exact rock as granite. It's just that this sample of rhyolite happens to have a lot more of the pink tannish colored mineral, that's potassium feldspar, and a lot less quartz, the colorless one, and you can just barely see black specks here and there, okay? But compositionally, it's the same exact rock, okay? It's just that rhyolite is extrusive, so it formed at Earth's surface. We're going to swing over to the other end of the spectrum in terms of composition. We're going to look at the dark colored rocks. These are called basaltic rocks because they contain predominantly silicate poor minerals, okay? Mainly the mineral plagioclase, feldspar, and then also more metals, mainly iron and magnesium, okay? That's where the term mafic comes from. So you'll hear of basaltic rocks also as the term mafic, magnesium and ferrum, iron. Okay, so they have a low silica content. And what you're seeing here is basalt. Okay, so basalt is the rock that predominantly makes up all the bottom of the ocean basin. So the rock at the very bottom of the ocean, that is basalt. Okay, that's an extrusive igneous rock, so it's very fine grain, mostly made up of a black mineral, and then to a lesser extent a greenish yellow type mineral called olivine. Okay, which here you can see this kind of greenish yellow mineral here in this rock called peridotite. That is the mineral olivine. Okay, so there's a substantial amount of olivine in basalt as well as this gabbro. You just can't really see it because the grains are so small, and this chunk of basalt just happens to have a lot more of the kind of black plagioclase feldspar. Okay. So really, as you're seeing, no two rocks are really the same, even the same type of rock. You go out at the ocean floors and you look, you're going to see basalt. All the rock is going to be basalt, but it's going to have different amounts of different minerals in it, okay, but still be considered to be all basalt. So that's what makes geology to be a little bit challenging for students, but just know that, you know, even though every sample is going to be different, they're all still classified as the same rock because they contain the same minerals. So we have the basalt, that's the extrusive variety with the small grains, and then we have gabbro, which is typically found beneath the basalt, deeper down in the ocean basins. That is the intrusive variety, and you can see the larger grains there. Kind of a middle ground in between basaltic and granitic are the andesitic igneous rocks. Okay, these are also referred to as just intermediate because they're right in between the composition of the two. So as you would expect that, intermediate rocks or andesitic rocks, they have around equal parts light colored and dark colored minerals. Okay, and compositionally as well, they're right in between the two. Silica wise, they're right in the middle as well between the two. So the easiest way to understand andesitic or intermediate rocks is that they are right in between granitic and mafic, just as you would expect. So what we're seeing here up at the top is andesite. Okay, that's a rock that forms the high peaks of most of the Andes in South America, hence the name andesite. That is the extrusive version of this, of the intermediate rocks. And then you have diorite. Diorite is the intrusive version. Oftentimes you'll find diorite makes up the cores, or like the foundation of huge mountain ranges. Okay. A lot of times if you go out west to the Cascade Range up in Washington, Oregon, you'll often find a lot of diorite that's been shoved up from deep down up at Earth's surface because of mountain building. So you'll find a lot of diorite, and then you'll find some andesite as well. For the Sierra Nevada, if you go out to California, that's predominantly made of granite. So you'll find a lot of granite out there. Okay. The Rockies are totally different, and we'll talk about that separately later. Okay, same thing with the Appalachians. And then ultramafic igneous rocks. Okay, so these are the most mafic. So they have even more dark colored minerals, and they're even more silica poor than just the regular mafic rocks. Okay, so these aren't as common, okay, and they tend to be found in just small areas when they are found. They're basically just not, they're pretty rare, let me just put it that way. But anyways, they are their own category because of their unique composition. But peridotite, of course, with the larger grains, formed as an intrusive igneous rock, and then komatiite, which is extremely rare, is the extrusive variety. Okay, so it can form at the surface, but like I said, it's very rare. Both require higher temperature and pressure as a general rule in order to form. Okay, so here's a chart that shows the 6 most common igneous rocks. So this does not include the ultramafic rocks that we just looked at. Okay, in reality, for this class, they're really not that, they're not important at all. They're just kind of there. But if you're going to learn anything about rocks, what you want to come out of the class remembering, or understanding at least, is the difference between these 6 rocks. Okay, so over on the x-axis, or on the rows, we have composition. Okay, so we have not rows, rather it would be columns. Okay, so composition is up and down. Okay, so we have granitic, andesitic, and basaltic. Okay, so we have high silica, middle silica, low silica. Okay, light, middle, dark. Okay, so that's the composition. Uh, for the rows, we have coarse grained and fine grained. Okay, so remember, intrusive versus extrusive. So notice the large shaped crystals and all of these intrusive rocks. Okay, so granite, andesite, basalt. And then the fine-grained or extrusive varieties that formed at the surface, so rhyolite, andesite, and basalt. So I talked pretty extensively about basalt and gabbro being ocean basin rocks, so they make up the floor of the ocean. Diorite and andesite, like I said, typically are associated with mountain building, so they're found in mountainous areas where mountain buildings happen. Granitic rocks, so granite, predominantly granite, but also rhyolite, those tend to be found, those are continental rocks. Okay, so all of the continents are basically, their foundations are made of granitic rocks, okay, granite and rhyolite. Okay, so here's just another way to look at the same, the last chart we looked at. Contains a little bit more information, but it's basically the same thing. So I'm not going to labor on it. It just breaks it down again, really by composition and then texture, and then adds a little bit extra information down here as well, like percent color of dark versus light. Just another way to kind of classify. All right, before we move on to talking about the actual formation of the rocks, are there any questions on the composition and textures? Nope. Okay. All right, well then let's move on here and we'll talk about Bowen's reaction series. So this is basically just, it sounds menacing, it looks menacing, but it's really not. It's actually quite, it makes sense, okay, once you understand it. So minerals will basically turn into a solid, okay, aka they will solidify at certain temperatures, okay? And we know from laboratory experiments that darker colored minerals, which again are the mafic ones, the silica minerals, they are going to solidify from a liquid melt or like a magma, a molten rock consistency. They're going to solidify at high temperatures, okay? So right here, about 1200 degrees, we're going to see the darkest colored minerals go from liquid to solid. They're going to solidify and settle out into the magma chamber. Okay, then as the magma chamber grows older and older, what happens is they naturally cool down. Okay, so over time, what we're seeing is that magma chamber cooling down, hence the magma that's in it is also cooling down. So as it's cooling down, we're seeing that the darkest minerals have already settled out. The chamber starts to cool down a little more. So kind of the light, darker minerals are gonna solidify and settle out. Then we see kind of the middle ground ones, kind of like the, there's not really any gray minerals. This is kind of a bad representation, but let's just say the middle ground colored minerals, okay? So not dark, not fully light either. So the middle ground minerals, they're gonna solidify and settle out at kind of like a middle temperature. And finally, we get down to about 750 degrees Celsius, which is basically the coolest that a magma chamber can get before all of the minerals are going to fully solidify. And those are the lightest colored minerals, so like quartz, that colorless quartz, that tannish colored potassium feldspar, muscovite mica we haven't really looked at, but that's a light colored mineral as well. Okay, so the basic gist is you're just seeing that dark ones solidify from the liquid turn into solid first at the higher temperatures, then the light ones will do that last at the lower temperatures. Anyway. We had a question. Okay, so which igneous rock contains mostly dark colored silicates, 45 or more? Okay, so I think you mean 45% silica, right? 45% silica or more. Well, it would be the opposite. The dark colored minerals, yes. Yeah, okay, so yeah, the dark colored silicate minerals have the least amount of silica. So they're gonna have less than 40, I believe it's 45%, but they're gonna have about the remaining 55% or whatever is going to be the dark non-silicate stuff, so like the metals. Okay, so just go back, let's see here. Whoop, I don't want to X out here. I didn't give the percentages because quite frankly, that's not really important. That's just, yeah. Yes, it is basaltic, yeah, the mafic one. So things that are really not necessary, I'm not going to specifically cover. But yeah, just so you guys do know that there is percentages that are associated with silica content, and those are listed in the book. I just won't cover them in the lecture because I don't. Memorizing those isn't really necessary for all purposes of this class, okay, an intro level class. Okay, but for undergraduate students, yes, that's super important stuff. All right, so does anybody have any questions on Bowen's reaction series then? That's, in my mind, pretty cut and dry, but it's a very important concept. Okay. All right, so related to Bowen's reaction series is something called magmatic differentiation. It's basically what I just described with the dark colored mafic minerals solidifying first at the higher. So that's these green ones. Okay, notice that they're solidifying and kind of settling down to the bottom of the magma chamber. Then you see these blue ones. Assume that those are lighter colored and more silica rich. So those ones are solidifying later when the magma chamber cools down a little bit, and then they're just solidifying on the minerals that were already there, which were the darker colored ones. Okay. Yeah, and so I guess what you're seeing is the evolution of the composition of a magma chamber, where up here in A, it's hot, the magma chamber is still hot enough where no rocks have solidified. Down at B, you can see some have solidified, they've turned into solid rock on the fringes on the bottom. And then you go to C, and a good majority of it has already solidified. So all you have left is probably the lightest colored silicate minerals. So the kind of end result of what magmatic differentiation is that magma in a magma chamber, as it cools down, its composition is becoming increasingly silica rich, because as its temperature is decreasing, that means that the darker colored minerals have already solidified and settled out, which means that they're not adding to the chemical composition of the molten portion of it. So which mineral is the last to solidify? It's always going to be the lightest colored one. So usually it's quartz or plagioclase feldspar. Typically quartz though, that colorless looking one. Okay. Any questions on magmatic differentiation? Okay. All right, well then let's go ahead and shift gears and look at sedimentary rocks. All right, so sedimentary rocks are just simply rocks on Earth's surface, and it can be any of the three types of rocks. Okay, igneous, pre-existing sedimentary or metamorphic rocks, any rocks that were already in place and formed that were weathered or broken down by the environment into smaller pieces, and then those pieces were transported somewhere else and then deposited in big piles and then later cemented together. Okay, so that's after the cementation occurs, that's when those sediments become a sedimentary rock. Okay, so about 75% of all rocks on the continental areas are sedimentary. Like I said, the foundation of the continents is going to be igneous, typically granite, but the majority of the rocks in the continents are sedimentary. Okay, sedimentary rocks are used pretty extensively to age date Earth's history because they often contain fossils. Igneous rocks, metamorphic rocks do not contain fossils because they get hot enough, or in the case of igneous rocks, they come straight from a melted constituency. So there's no way that any organic material, including bones, is going to be able to sustain those kinds of heat. Okay, so since sedimentary rocks never really get hot, they don't. The fossils within will tend to be stored and retained. Okay, now sedimentary rocks can be turned into metamorphic rocks, in which case, we'll talk about that next. If that happens, then yes, the fossils will be destroyed. Okay, but sedimentary rocks that are produced and just left there and not touched again, yes, they will retain an abundance of fossils, and those fossils can tell a lot about Earth's history. Okay, so we're going to talk about that when we look at Earth's history or Earth's evolution. That'll be in right before spring break. Also, sedimentary rocks are important sources of petroleum, natural gas, and coal. Also, just general building material. So just think like stones, crushed up gravel that goes into cement, things like that. That's all important building material. And then also sedimentary rocks can be sources of various metals, and then table salt we saw, of course, with halite, the mineral halite. There's a lot of uses of sedimentary rocks, okay? And we have plenty here on the continents. Ocean basins, different. That's different. Okay, that's just strictly usually igneous rocks with sediment on top, just sediments sitting up on top. All right, so sedimentary rocks form via the process of lithification. This is just simply compacting the sediments and cementing them together with a cementing agent. And that happens naturally. So by compaction, what I mean is usually when sediments are deposited in a certain area, there's a continual supply that's being brought in and dumped. And so as you bring in more material and dump it on top of the stuff that was already there, what you're getting is added weight. And added weight results in compaction. So that's how the compaction part of lithification occurs. Cementation occurs generally through surface and groundwater, because surface and groundwater contain dissolved, or what you might call invisible. You can't see dissolved constituents in waters because of the pH change that happens with dissolved constituents. The solid portion does actually go into a dissolved state, and you can't see it, okay, but it's there. So with cementation, usually natural waters contain these dissolved cementation agents like calcite, iron oxide, silicon oxide. They're all, again, in a dissolved state, so you can't see them. But what happens is they will intermingle in these spaces in between the individual grains. And then usually what's called a phase change will occur. They will basically go from dissolved to becoming a solid. Okay, and then once they become a solid, they essentially turn into that cementy type kind of like some, if anybody's ever felt fresh cement, that's kind of how it is. It's literally like cement. It's got that cementy kind of feel to it. That will eventually dry out, and then all those little grains will be cemented together. So that's pretty much how lithification works. It's also nothing that's really anything outrageous. So what we're seeing here is an example of how coal forms through the lithification process. Okay, and this is really actually pretty cut and dry too, where since coal forms in swampy environments where there's standing water, and that water tends to be very oxygen poor. Okay, it's important to understand that when an area is any constituency such as water, standing water, is devoid of oxygen, that means that it dramatically reduces the opportunities for decomposition to occur. Decomposition requires an abundant amount of oxygen in order to undergo its process. And so when you go into a swamp, basically, all the living material, the carbon material, living material will die. It'll fall down to the bottom of the swamp in the water. It'll get covered with water. And then because there's not much oxygen, most of it won't decompose at all, okay? And so over time, more and more plants die, cover up the old plants, and so you're adding more weight, okay? That's compacting, which is what you're seeing here. And you just keep repeating that process over and over again until eventually you've got a lot of compaction. And then there's, just like any natural water, there's going to be certain constituents in the water that are dissolved that will create a cementation agent eventually to cement all that stuff together. Okay, so the process goes from peat, which is basically pretty much just newly decaying organic material like plants and whatnot, to lignite, which is on its way to coal. So it's a very compacted form of peat. And then to bituminous coal, which is the sedimentary version of coal. The next step down is anthracite, but that occurs only if bituminous coal is metamorphosed. So we'll hold off on talking about anthracite until we look at metamorphic rocks. Okay. So sedimentary rocks are split into two basic groups, detrital and chemical. Okay, we're going to look at these two here next. Detrital is basically sedimentary rocks that are made out of solid materials that were basically wet and deposited in a big pile, and then later turned into rock. Chemical sedimentary rocks, they form from dissolved minerals, minerals that were once dissolved within waters, but then later precipitated and were cemented together as a solid rock. So first we'll look at detrital rocks, some of the most common ones. So we have conglomerate and breccia. These are basically siblings. Okay, conglomerate forms in a stream environment where there's running water. Breccia forms in areas that does not have running water, so mainly mountainous areas. And how do we know? If you look at the larger grains that are mixed, kind of encased in the smaller ones, here with the conglomerate we can see well-rounded stones, and that implies water was involved, because water over time nicks off the rough edges of rocks, making them smooth. Now down here with breccia, we can see that they're jagged and angular edges, so we know that water did not play a role with forming this specific rock. Okay. Now, both of them have the larger grains kind of sitting in a kind of a hodgepodge of sand or silt-sized materials. Okay, that's called a matrix, the smaller material that holds up the larger grain, that's a matrix. But basically, yeah, those tend to be like sand silt sized materials, which are found in both environments, both mountainous areas and streams. Sandstone is pretty cut and dry type rock. So this sample of sandstone, how it naturally would have formed, you would have to look at it tilted about 45 degrees to the right. Okay, so you see these kind of stained lines. Those are what's called bedding planes. Basically, the stain material, the stain colors themselves are called impurities. In this case, probably iron oxide because it's kind of orange color. Those will typically stain through samples of rocks, especially like out west with sandstone. They'll kind of stain between individual layers, and individual layers always form flat, okay, with a few exceptions that we'll look at later on. But typically, well, at least with water formation, they form flat. And so what you're seeing is basically layering, okay? And the constituent material is sand-sized, okay? And it's quartz. So it's sand-sized quartz, essentially. That's what sandstone is. So sandstone typically forms in either beach or sand dune environments, so beaches or deserts. Then you have shale. Tends to be a darker colored, very fine grained rock that forms slow moving, sediment rich, but also oxygen poor type environments. So mainly lakes and backwaters, but not full fledged swamps usually. Yeah, typically lakes. You know, lakes is just a good way to explain it. So the dark colors because of the lack of oxygen, called an anoxic environment, lacking oxygen. So fossils are often found in shale because they form in lake environments. Obviously, it's not surprising to see that this sample has a fern that's a fossil in it. So that's typical. With chemical sedimentary rocks, those again are rocks that's sedimentary rocks derived from material that was once dissolved in solution. Okay, so it means you can't see it in the water, and as a result of changes in pH, it precipitated to form a sediment. Now again, precipitated means just to go from a dissolved state to a solid. So it turned from invisible to solid, and then formed sediments. That change in pH, this process is pretty common for limestone or the mineral calcite, which is high up on the basic scale, and natural waters tend to be pretty much neutral on the pH scale to slightly acidic. And so as a result, oftentimes calcite is dissolved in waters, and it will undergo a slight change in pH before calcite will actually precipitate out and turn into actual limestone. Okay, so also with limestone and dolostone, which is pretty much a sibling of limestone that includes just one atom of magnesium, and that's the only difference. So limestone and dolostone, pretty much the same thing. They will, when they solidify, they will solidify into what's called like a calcium mud, or like a calcium ooze. There's many different terms to describe it. I prefer just to use mud. Basically, it is like a mud or cementy, cement-like consistency. And then what happens is, since limestone is pretty common in like warm shallow sea type environments, like the tropics, there's a substantial amount of life there, and what will happen is when life dies, their shells will just drop down into this lime mud or this calcite mud, and then eventually get incorporated as a fossil. So that's kind of how limestone typically formed. Okay, so I guess I went a little bit ahead of myself here talking about limestone. But basically, like I said, yeah, forms in warm, shallow seas. So think like the Caribbean, present day. There's a substantial amount of limestone all over North America, west of the Appalachians, because at many times in the geologic past, because of plate tectonics, North America has actually been centered on the equator multiple times in the past for millions of years at a time. Thus, a lot of North America was actually a warm, shallow sea. So it was like the environment around here was once very Caribbean-like. And so, coral reefs, limestone, very lush life, lots of fossils, etc. And then, as I said, with dolostone, the only difference is dolostone is essentially, it's made of the mineral dolomite, which is the same thing as calcite, but it just has one atom of magnesium added to it. It's the only difference. Okay. Chalk is very similar to limestone, except that it's made up of microscopic algae. Okay. Forms in a very similar process. Very similar type places, so like a warm, shallow sea type environments as well. Chert. Okay, so chert is what's called microcrystalline quartz. And microcrystalline just means very fine in size, so like glassy. And typically with chert, if it's colorless, you can often see through it. The colors often inhibit, so you can't really see through it, but very fine grain and very fine detail oftentimes, usually layered. You might also know chert as flint, jasper, or agate. Those are all the same things. Very hard on the Mohs scale, so you can actually chip them. I mean, they're soft enough where you can actually chip them with a blunt object and make a very sharp edge. So hence, like arrowheads, former cutting tools from ancient civilizations, they've used chert for thousands of years as tools, and rightfully so, because it's a very hard and good tool to use. See, chert does have a biochemical origin as well, very similar to chalk, and where it's made up of siliceous microorganisms that are found in oceans even present day. So you also have banded iron, which is this bottom colored rock. You notice that it's layered. Okay, so layered means banded, or banded means layered rather. And you just see alternating layers of chert and iron. That's all it is, alternating layers. Okay, then there's evaporites. Okay, so in rock form, if you put multiple individual minerals of halite or gypsum together, technically they become a rock, but just so as not to confuse anybody, we learned halite and gypsum as minerals, okay, which is true. That's really how they should be classified. But once you start to get multiple, like big, large chunks of them, that's when they can technically be considered a rock, okay, but that's really a gray area, and I'm not going to we're not going to go there in this class, okay? So I like to honestly think of the halite gypsum as just minerals, but just know that yes, that's a gray area. They can be considered rocks if they have many crystals included in them. And then bituminous coal. Okay, so we already talked about how that forms. So swampy environments, the woody material, the woody carbon material dies and it gets buried, and then basically undergoes compression and cementation and turned into coal. So lots of coal left in the Appalachians and out west in the Powder River Basin in Wyoming, but as you'll probably see over the next decade, coal is really on its way out the door, and that's because natural gas just has been a lot cheaper over the last 5 years or so. So I think coal is probably a dying industry on its own. So anyway, we will see, I guess, how that one turns out. Let's check to see if there's any. Nope. Okay, so we have nothing in terms of questions. So here's a chart of the classification of sedimentary rocks. Basically, they get the detrital rocks mainly get classified by size of the individual little particles, the individual sediments. So coarse or large up here, very fine to the point where you can't see them. Those typically are classified just as muds. Okay, so like mudstone, shale. Then you have the chemical and organic sedimentary rocks. Coal is really the only organic sedimentary rock because it contains organic material, so aka carbon material. The rest are chemical. So you'll notice that most of these that are made of calcite can just generically be referred to as limestone. Even chalk, for really all intents and purposes, can be lumped in there, though it's slightly different in composition because it's actually made from microscopic life. Then you got quartz, other stuff that's really not that important. Some of these limestones are really broken down by how much shell component they have, or how much fossil material compared to the limestone mud that I talked about. So like crystalline limestone is pretty much 100% limestone mud. That would be like picking up a piece of limestone and there being no fossils. It's just all calcite. That's kind of the limestone mud. Versus you come down here toward coquina and fossiliferous limestone, and of course they have substantial amounts of shell material and a lot less of the mud constituency. Okay, so you'll probably you'll see different versions if you pay attention when you're out at the beach or look next to rivers walking or whatever. If you pick up some limestone, you'll see differences if you're keen to it. Okay. Are there any questions about anything from sedimentary rocks that we just looked at? Okay. Well, then let's go ahead and we'll wrap up with looking at metamorphic rocks. Okay, so metamorphism is just simply changing a rock's mineralogy and its texture by adding heat and pressure. Okay, so that in itself, that definition is pretty cut and dry. Basically, metamorphic rocks can be produced. Metamorphic rocks we know come from a pre-existing rock, and it can be any pre-existing rock of any of the three types. It's just that you take a pre-existing rock and then you subject it to heat and pressure, thus it becomes a metamorphic rock. Okay. One important thing to metamorphic rocks is that they are never melted during the heat and pressure process. Okay. If they did, they would become an igneous rock. So having just said that they never melt, okay, let's talk about the heat and the pressure. Okay, so there's really degrees of heat and pressure that can emanate from an environment in an area where metamorphic rocks are forming. Okay, we can have low grade and high grade metamorphism. So low grade is basically just where you have lower heat, lower pressure. As a result of the both being lower, typically minor mineralogy changes occur. Mineralogy and so basically minor chemical and chemical and texture. That's it. Minor chemical and texture changes will occur. Okay, with high grade metamorphism, you're looking at higher heat and higher pressure. So we're looking at, of course, more major changes to occur to texture and composition. Okay, so you have those two different, the high grade and low grade, the different degrees of metamorphism. But now we're going to look at the two different types of metamorphism, and then as you can see, when I go through and describe these two different ones, you're going to see that they each are going to emanate as either higher degree or lower degree. Okay, so contact metamorphism is the first type. And this occurs a relatively localized scale, so pretty, not large in scale at all. Okay, we're talking, an area around a magma chamber, which can be pretty good sized, but grand scale magma chambers are pretty small compared to all the land on Earth. So around magma chambers, around volcanic areas, things like that, but typically around lava chambers, or excuse me, magma chambers, in which this is kind of orangish, reddish yellow is actual magma in a magma chamber. And what you're seeing above it is this gray rock, which is essentially cooled down rock. Okay, so this would probably be more mafic rock that's recently solidified from this magma chamber itself. Okay, and then you see this kind of purple stuff. Well, those are rocks that were pre-existing, but they've gotten heated up enough where they're being metamorphosed. Okay, and what's happening is in the process of metamorphism, water that's trapped in the crystal structures of rocks will go from will actually be heated up to the point where it becomes mobile as a steam, basically steam. And so then it starts to move around within the crystal structures. And oftentimes, in addition to that, if hot enough, it's the steam that can actually change the mineralogy or the composition of the minerals. Okay, so that's what you're seeing in the purple area. That is the actual contact metamorphism that's occurring. So pre-existing rock that's being heated up, and to a lesser extent, there's only a little bit of pressure being exerted. So with contact metamorphism, we're dealing with usually a decent amount of heat, but usually a relatively low amount of pressure. Okay, so essentially the rocks are being baked. That's what the purple ones are being kind of baked. Okay, then we have the large scale metamorphism. That's called regional metamorphism. This occurs in mountain building processes. Okay, so think like Rockies, Sierra Nevada, Cascades, Andes. Regional metamorphism would have occurred along the extent of all those mountain ranges, the extent and the width. Okay, it's a pretty large scale. This is when there's directed pressures from movement of different tectonic plates. Okay, so I know we haven't talked about plate tectonic, but we're going to, I believe, next Wednesday. Just know that tectonic plates move, and they often. I'm sorry, what was that? So tectonic plates move and crash into each other, and that's typically how mountain ranges are formed, is by crashing into each other, and that drives mountains upward. But in the process of driving mountain upward, there's a lot of pressure and there's a lot of heat that's produced. Okay, and so regional metamorphism is typically associated with the high grade metamorphism, the high pressure, high heat. And so this is where we typically find the most metamorphic rocks, is in and adjacent to mountain ranges. Okay, metamorphic agents. Okay, so the main things that really drive metamorphism are pressure, heat, and the presence of fluids, mainly water. Okay, so like I already explained the concept with water turning to steam and migrating around. Okay, heat is pretty self-explanatory. Generally, the heat comes from the magma that's present, or in the case of regional metamorphism, heat can also be generated just from the plates smashing together through friction. That provides pretty good amount of heat as well. The pressure comes from, yes, from the plates smashing together as well. Now, there's two different types of pressure. One is where I call it confining, where you just have weight from above that's pushing downward. Okay, that's just simple confining pressure. Differential stress is a type of pressure where you have, imagine a box that's a square, and you've got 4 sides and then a top and a bottom. Okay, imagine just of those 6 sides, you have 2 sides that are really putting a lot of pressure on that box. So what's going to happen is that box is going to deform from box shaped to more of like a egg type shape because of that uneven pressure. So that's what differential stress is. Okay, and you're going to see it here when we talk about foliated textures. So with foliated texture, we have basically, it looks like an igneous rock where there's been no or very little pressure pushed against it, against the individual minerals. So that looks like a normal rock. Now with a foliated rock, you can see that there's uneven pressure from 2 of the sides, which are causing a flattening out appearance of these minerals into also what looks kind of like a layered appearance. And it makes it kind of look egg-shaped in a way. Egg-shaped is probably not the best way to describe it, but it elongates them and makes it look layered. That's the important part. Okay, we are quickly running out of time. I think I only got a couple more slides. Talk about the different rocks. I might be able to make it, we'll see. So grades of metamorphism, or the increasing metamorphic grade. So basically, with this slide, all it is with additional heat and pressure, you go from one step to the next. So slate, shale is sedimentary, okay, but slate is basically metamorphosed shale. So you add some heat and pressure to shale, you'll get slate. Add some more, you get phyllite. Add some more, you get schist. Add some more heat and pressure, and you finally end up with gneiss. Okay, so that's kind of what the metamorphic grades means there. And then lastly, look at the individual, some of the rocks. So slate, like I said, is made from a shale. It's planar, like shale is, very fine grained. Schist is kind of an oddball, often contains a mineral that's kind of sparkly, but basically when you add heat and pressure to slate, you'll often get schist. Then gneiss is kind of considered to be the end of the road most often for the metamorphic rock sequences, because any more heat, it'll melt, basically turn into igneous rock. But notice it's got the banded appearance. Okay, so it's, as to say, it's foliated. Marble is basically metamorphosed limestone or dolostone. Quartzite is metamorphosed sandstone. And then anthracite coal, like I said before, is metamorphosed bituminous coal. Okay, notice that it's got that really dark, shiny appearance. That comes as a result of metamorphism. Okay, so here's the classification of the metamorphic rocks, mainly separated by foliated versus non-foliated. Okay, and for the foliated rocks are the ones that have the foliation. You can see here's the increasing metamorphic grade for the most common ones. Okay, so that's there for your look and view before the test. All right, so quickly I will go see any comments. Nope, not any comments. Are there any questions? here. Okay, so then what I'll do here real quick. So for next Wednesday, when we meet next, okay, chapters 4 and 5. So we'll look at plate tectonics, earthquakes, and Earth's interior. So make sure you read chapters 4 and 5 of the textbook. Watch Earth Revealed videos number 3 and 6, and then we will resume. So with that, I'll let you guys go for the week, and have a great weekend. See you on Wednesday.
Have a good weekend.
All right, thank you.
Thank you.